In the previous module, we talked about sum of the min terms and product of the max terms forms of representations. Now, these representations not necessarily always result in lesser hardware. In this module, we will talk about how do we minimize a logic circuit so that the hardware required for the implementation becomes minimal. There are different tools available for Boolean function implementation. We will talk about one such tool, which is a graphical tool called a Karnaugh map. How do we use this Karnaugh map for minimization of Boolean function, and how do we get a minimal circuit for a given function? The objective here is to find out optimal gate level implementation of a Boolean function which describes a digital circuit. When we say optimal gate level implementation, the aim is to have lesser number of logic gates as well as lesser number of inputs per gate if possible. We will use Karnaugh map as a tool to do this minimization of Boolean function. Now, K map is a graphical device which is used for simplifying Boolean expressions. Like a truth table, these maps relates inputs to the outputs, and this technique is useful for circuits up to 6 input functions or 6 input variables. Beyond that, because of a graphical tool, visualization becomes difficult. So, we go for algorithmic tool for functions having more than 6 variables. So, let us see what is this K map and how do we use it for minimizing Boolean functions. K maps are used to produce expressions for a given function as minimal sum of the product expression MSP. When we say minimal sum of the product terms, there are two objectives associated with that. One, minimal number of product terms. There are minimal number of product terms. Each product term will result in a gate which is an AND gate. Lesser the number of product terms, lesser the AND gates required for the given circuit. The second objective is each product term has to have minimal number of literals. Whether it is a 2 input AND gate or n input AND gate depends on how many input literals are applied to a gate. Lesser the number of literals, lesser the number of inputs required for a gate. That means, if we combine these two objectives, a product term having lesser number of literals and lesser number of product terms, that results in minimal sum of the product expression for a given circuit. The circuit this produces minimal 2 level implementation, lesser hardware used for the given circuit. In order to do that, we will use a K map, which is a graphical tool. The way we are going to do here is, given a truth table, plot a K map for a given function using the truth table given. We know truth table will have rows, number of rows depends on the number of input variables. So, when we convert a truth table into a K map, row of a truth table correspond to a square in the K map. While plotting the map, we also ensure that adjacent squares in the map differ only in one variable. I will explain to you with the help of an example. So, let us look at an example of a function having 3 inputs x, y, z and an output f. The given function, all the input variables, all the combinations of the input variables are plotted and the corresponding output values are also plotted here. Since it is a 3 variable function, these 3 variables can have 8 possible combinations. So, there are 8 rows in the table representing different values of the input combination. As we mentioned in the previous slide, when we convert this truth table into a K map, each row of a table represents a square in the K map. Since there are 8 rows, the corresponding Karnaugh map will have 8 squares for this particular example. So, if we plot the K map, the way we are going to plot the K map, if you look at the Karnaugh map consisting of 8 squares starting from here to here, each one of them corresponding to one of the input entries. So, this is a square corresponding to input variables x equal to 0, y equal to 0, z equal to 0. So, what I represent inside this square is this square correspond to input x equal to 0, y equal to 0, z equal to 0, therefore, we call this as x bar, y bar, z bar, which is one of the min terms. Now, while plotting, we also said adjacent squares differ only in one variable. So, therefore, the values of x or x can either be a 0 or a 1, that results in two different values. Y and z can have 4 possible combinations 0 0, 0 1, 1 0 and 1 1. But while plotting in the map, we try to plot them in such a way that adjacent squares differ in only one variable. So, if y and z are taken, both are 0 0, then we will have a 0 1, only one variable is changing, then we make it 1 1. So, z remains as it is, only y is changing, then we make it 1 0, y remains as it is, then z is changing. So, the way we plotted the map here is corresponding to y and z, we are going to plot 0 0 first, 0 1 next, 1 1 third and 1 0 fourth. We said adjacent squares differ in only one variable. If you look at any square inside, for example, if you take this square here, this is a square corresponding to x 0, y 1, z 1 as represented as x bar dot y dot z. If you take another square here, this corresponds to x 1, y 0, z 1, that means x dot y bar dot z. Each square in the K map represents a row of my truth table, and corresponding input variables identify the square of the K map. Another way to tell is, in the K map, each square corresponds to a min term. For 3 variable function, there are 8 min terms possible, m 0 to m 7. Those min terms are listed in the K map as squares of the map. Instead of writing x bar, y bar, z bar as a product term, we could also write it as m 0 as a min term corresponding to x equal to 0, y equal to 0, z equal to 0. That is what is shown in this K map. So, therefore, each square in the K map represents a row in the truth table. But then what do we fill inside those squares? We will fill inside those squares corresponding output values for the given inputs. That means, for the first row in my table, x equal to 0, y equal to 0, z equal to 0, corresponding to x bar, y bar, z bar in my K map, output value is 1. What we enter in the K map, output value corresponding to the input combinations. So, if my input x 0, y and z 0 0, so x bar, y bar, z bar, for which output is a 1 is represented here. Therefore, we will fill all the corresponding outputs into the K map entries 0 1, 1 1, 1 0. The second row is x bar, y bar, z. The corresponding output is a 1. The third row is x bar, y, z bar, output is a 0. The fourth row is x bar, y, z, output is a 0. Fifth row is x, y bar, z bar, output is a 0. Sixth row x, y bar, z, output is a 1. Seventh row x, y, z bar, output is a 1. And the last row x, y, z, output is a 0. That means, inside the squares in the K map, we plot the corresponding output values. So, what we have done here is given a truth table, plotted the corresponding K map for the truth table. That is the first step in the minimization of the Boolean function. The second step is, having plotted the K map, using the K map, try to minimize the Boolean function. So, there are certain rules to be followed in minimization using K map. The rules here are, having plotted, form groups in the K map where the groups will consist of squares with value of logic 1. While forming groups, since it is a graphical tool, have a visualization in which only rectangular groups were formed and these rectangular groups will consist of the minterms which are a power of 2. So, I could have a group of 2, I could have a group of 4, I could have a group of 8. So, form groups which include minterms as power of 2. Only form groups of those entries where the output value is a 1. Ensure that all the ones in the map are included either in one or the other group. If you follow this while forming the groups, then it will result in a minimal function. So, let us look at the same example, the one we plotted earlier. The input functions are x, y, z and the corresponding outputs are plotted here. We will try to form the groups now. For example, when I say forming a group, look at the entries where the outputs are a 1 and form them a group in such a way that the group is having number of minterms which are a power of 2, and they should be adjacent entries. For example, I have an entry 1 here and a 1 here. I say I could combine these two as a group, which is a group of 2, which is a valid group. I have a 1 here and I have a 1 here. The question is, are they adjacent? Now, adjacency can also be obtained by, if we take this as a sheet of paper and wrap them around, which means this entry and this entry become adjacent to each other. So, I will have another group formed by combining these two ones. Now, are there any ones left out? No, I have taken care of all the ones. So, what we did here is formed groups which are including the output columns corresponding to ones. While forming the groups, make sure that the squares are adjacent to each other, as well as the groups having number of terms which are a power of 2. So, I have two groups each having 2 entries. That is the second step in minimization of the Boolean function using K-map. Now, having formed the group, let us look at a group. So, we have a group here with 2 entries, both are 1. If you look at the values for x, y, z in these 2 entries, the first one results in x is a 1, y is a 0, z is a 1. The second one results in x is a 1, y is a 1, z is a 1. If you combine these two, you will find x plus y bar is z, x plus y is z. By the basics of the Boolean algebra, I could write this as x dot z into y plus y bar equal to 1. So, what it results in x dot z. Combining these two results in a product term having only 2 literals, which is x and z. That means, a group of 2 will help you to drop a literal. If we have taken these 2 entries independently, you would have end up using one AND gate with 3 inputs, another AND gate with 3 inputs. Combining these two, we result only in a single AND gate with 2 inputs. And a similar way I can write for these 2 entries, x is a 0, whereas y is a 0 here and a 1 here, z is 0 in both. Another way to look at it, see which variable is having its value changed in the given group. For example, y changes from 0 to 1, so I will drop y, whereas x remains the same all through, z remains the same all through, both x and z are 0. That means, I will write that as x bar dot z bar. That means, the given function now, if I call that function as f, will consist of 2 product terms, x dot z plus x bar dot z bar. I require an AND gate here, I require an AND gate here and one OR gate here. So, we get a 2 level implementation consisting of 2 AND gates and an OR gate for the given function implemented. If we do the same implementation using some of the minterms representation, you would end up using 4 AND gates, each having 3 input functions and an OR gate. Instead of that, we are using 2 AND gates and an OR gate. So, K-map helps to reduce the given function into lesser number of gates. Let us look at an example with 4 input functions, 4 variable function. The function with 4 inputs are plotted here. A few points to note down here is, while making groups, since each group presents a product term, make as few groups as possible that result in lesser number of product terms being generated. Each product term requires a gate. The second observation is, while making a group, make a group as large as possible, because more the number of entries inside a group, lesser the number of literals used for the product term. But while doing so, ensure the rules are followed. Only group the adjacent ones, only make rectangular groups, only have groups of size which are powers of 2. At the same time, ensure these 2 points are also taken care of, then we get the minimal sum of the product function for a given function implemented. So, let us look at this example. We will try to form the groups here. So, we have identified one group with 4 ones. We could do that for the remaining entries. Now, if you look at the 4 corners, if we fold these sheet left and right, top and bottom, these 4 corners will become adjacent to each other. So, we get another group of 4. I will call the first one as a group 1, second one as a group 2. Now, we are left with, we have to ensure that all the ones are covered in group 1 or the other. We have already covered 8 ones, there are 2 more ones pending. We could form these 2 as a group, which results in another term corresponding to group 3. Now, are there any valid groups possible in this map? For example, these 2 1 are adjacent to each other. So, it is a valid group, but we are not going to include this group because this becomes a redundant group. If we want to include this, this will result in an additional product term, but this group has 2 ones which are already included in some other groups. So, I say this is a valid group, but a redundant group, so not to include that. So, we need to observe this. There could be valid groups, but redundant, so avoid them. Can we form a group of 2 by including these 2? Diagonal adjacency is not allowed, therefore, we say this is not a valid group. Can we form another group with these 2 ones and these 2 ones, they are adjacent to each other when we fold it top and bottom? Yes, it is a valid group, but as I mentioned to you, this becomes a redundant group because these 4 ones are anyway covered in other entries, so we need not have connected this. So, this is what we need to do from the map. Make groups of a larger size which includes entries with ones, have as less a group as possible, but ensure that all ones are covered in one or the other group. Now, having done this in this example, we finally get 3 groups formed here. Now, we could write the product term corresponding to each of those groups. For example, group 1, by observation we can see in this group W and X both have its values changed, somewhere it is 0, somewhere it is 1. So, we drop both of them, whichever variable having its value changing in a given group, we drop them, keep only those literals whose values remain constant throughout the group, which in this case Y and Z both remain 0, 1 throughout. Therefore, the product term coming out of this will be Y bar Z. So, for a 4 variable function, a group of 4 results in a 2 literal product term. The second group are the 4 corner ones. If you look at the values of W, X, Y, Z, you will find W having its value changed from 0 to 1. So, we drop them, whereas X remains 0 all through, we keep them. Y have its value changed from 0 and 1, we drop them. Z remains 0 all through. So, the product term corresponding to group 2 is Y X as 0, Z as 0. So, we get X bar dot Z bar. Again, a group of 4 results in a product term having 2 literals. The third group is a group 3, in which W and X both remain the same 1 1, Y also remains as 1, whereas Z is changing its value. That means the product term will be W dot X dot Y. A group of 2 for a 4 variable function results in a product term having 3 literals. So, we got now 3 product terms, Y bar Z plus x bar z bar plus w dot x dot y, that becomes the minimal function for a given 4 variable function represented and then plotted using a K map. We could convert this into a logic circuit using gates, which will result in a 2 level implementation and or a NAND. That means K maps, if properly applied the rules, groups formed properly, end up in a minimal gate level circuit for a given function.